So last time we were at various ways in discussing parallel performance metrics. And the classical ones, which we will take more, we will discuss a little bit more, are actually the speed up and efficiency. But of course, the primarily metric is the time, since we would like our experiments in parallel to be as fast as possible. So what I was saying is that we can think about the speed up. It is the time which a certain algorithm needs to be executed on one processing element divided by the time of the same algorithm or another algorithm, which is parallelized and run on p processing elements. And I was mentioning that actually you may have even two different algorithms, one on one processor and another one on a parallel processor, or for parallel implementation. And then in one case, we can talk about the relative speed up for the same algorithm and absolute speed up for different algorithms. Why I am mentioning this? Because sometimes when we choose an algorithm to implement on a parallel platform, we think about how much the algorithm, uh, uh, what kind of degree of parallelism the algorithm has. And um, um, this by no mean um, could be the fastest algorithm on one processor. So when we improve the algorithm, we may sometimes get a worse speed up, thinking that numerically inefficient methods scale better. And this is wrong. This is a wrong thought, because we should we should really think about numerically efficient methods and try to parallelize them. Of course, we sacrifice something, but um, we should not really sacrifice numerical efficiency for parallelism. And this one message I find very important, and that's why I'm mentioning it. So, since I'm a bit pressed in time, I suggest you go through more carefully with the slides on this topic. I'm not going to say much about this, but you can see why actually, if you think about relative speed up, you may end up when you're improving the algorithm, you may end up with a worse speed up. So when we improve an algorithm, in order to run it faster, we change the proportion between a serial part and a parallel part. And this is the reason which is behind to sort of improving an algorithm and getting a worse speed up. For the algorithms you are going to implement in the course, you will not observe that. But in general, where you have a big choice of algorithms, it may occur. So it's our responsibility to choose the right algorithm and, of course, implement it in a good way. So efficiency, I just mentioned, this is a measure which is supposed to tell us how well we use the parallel computer resource. And the close the efficiency to 1 is, the better. So there was a certain trend in research where we could pose the task to relate the number of processing elements we use to the algorithm so that we preserve a certain efficiency, say of 75% or something like this, for all our choices. And we have on one side, of course, an algorithm, the number of processing elements. On the other side, we have something which relates how much computations, how big our problem is, and try to relate n with p to keep efficiency good enough. So, about scalability, you see that we can consider scalability of the machine itself, which means that adding more resources the interconnection network will still function efficiently. So it can incorporate more and more processing elements without degrading the communicational speed. We can talk about scalability of an algorithm, and as it is indicated here, generally, um, an algorithm will scale if we use more and more resources and we minimize the idleness due to imbalance and computational overhead. But of course, I think it's very important to think about scalability of machine algorithm pair because, as I already mentioned, not all algorithms will perform equally well on all computer platforms. And the good match is, to a certain extent, our responsibility to know what machine we have in hand and how an algorithm may may perform on that. So, um, about scalability, if you look around, you'll find a lot of different definitions. I leave it to you to read, but somehow this is the ideal case we think about. So we take um, we have a problem to execute, and we try to um, increase the number of processors. And so if we do that, so we sort of think that the parallel execution time will remain constant if we increase at the same time the number of processing elements we use and the size of the problem. So the ideal case is never reached. So the parallel execution time can never be constant because we have the communication overhead. And how this communication overhead grows when we increase the amount of resources we use and the number of and the size of the problem. Yeah, we always see some communication overhead, but this is a kind of guidance we would like to see. And I will show you an example of an algorithm run on a parallel machine with some timing, so we can see and judge whether it scales fine or not. Um, So regarding to scalability, we have two cases, and those two cases you're going to consider in your reports. The first one is we talk about fixed scale speed up or strong scalability. So what we do, we have a problem with a fixed size and we increase the number of processing elements we use. And we hope that once we take twice more processing elements, our time will decrease twice, ideally. The other one is scaled speed up, which is also known as weak scalability. So we look at what happens with the performance when we increase at the same time the size of the problem and the number of processing elements so that we keep the the load per individual processing element large enough and approximately constant. So if we increase both size and number of processing elements, and we keep the local uh, amount of work per processor the same, we would hope that the time will be almost the same. Again, I'm talking about ideal cases. And in the reports, you are going to include both tests, strong scalability test and weak scalability test, and see how your implementation scales. So I want to say something about, so these were measures. I want to say something about parallel performance models. And we go back to year 65. So we see a very famous person, Gene Amdahl, who was a chief engineer at IBM. And we see him in 2008. So he passed away in 2015. So he was alive not so many years ago. So he has a profound impact on the parallel, on the development of the parallel computations. And I want to read this quote from him, which is from 67. So I read it aloud. Over a decade, prophets have voiced the contention that organization of a single computer has reached its limits and that truly significant advances can be made only by interconnection of a multiplicity of computers in such a manner as to permit cooperative solution. The nature of this overhead in parallelism appears to be sequential, so that it is unlikely to be amendable to parallel processing techniques. Overhead alone would then place an upper limit of throughput on 5 to 7 times the sequential processing rate, even if the housekeeping were done in a separate processor. At any point in time, it's difficult to foresee how the previous bottlenecks in a sequential computer will be effectively overcome. And so this gave rise to Amdahl's law, which is the most pessimistic performance model. So I'm going to show this. Here it is. Um, what it says is that we have a number of operations and they are grouped in a number of subtasks which can be done um, sequentially. So we can parallelize the work in each task, but those tasks would be done sequentially. And then you make a simple computation on time, which is the sum of all t's to be done in on each subtask, and then you do it with certain rates, and then you see that the average rate is inversely proportional to the serial part. So P is the parallel part of my algorithm. 1 minus P obviously is the serial, since I have 1 as the total amount of work. And I see that the average rate is inversely proportional to the serial part. So the speed up is bounded whatever we do by the serial part. That's Amdahl's law. And you have to be very careful when you write in your reports that you use this law, because I think it is not really the way how we should think about this. So let's see what happens. Now, this is the example. We have a highway of 300 kilometers, total 250 on a highway. You drive your car with 200 kilometers per hour, and then you have 50 kilometers, not the highway with a lower speed, and then you see that your average time is really not very impressive. Now, it took about 20 years to actually break through the Amdahl's model and show that it is not truly correct. And it happened in 1988 when they already had a parallel machine. It is a 1024 processor N cube 10 at that time. So you see, although Amdahl was profiting that the parallel computations are leading to a dead end, people's curiosity didn't stop, so they were producing parallel computers at that time. And then in this year they showed that the speed up can be on this number of processors can be much higher than Amdahl's law predicts. And then they started trying to find another ways of modeling the parallel performance. We don't really have time to go through, although I have included them in the slides. So there is the Gustafsson-Barsi law, and they try to exactly look differently on the serial and a parallel part, so that we do not see Amdahl's law, which is once more very pessimistic. One thing I want to mention about this is, once more, when you run your program on larger resource, one reason which is not at all in Amdahl's law is that you change the proportion between serial and parallel part. And this is one of the reasons to get better performance than Amdahl's law predicts. Another difficult part with this model would be that how can you determine in a good way what is your serial and what is your parallel part? But these are details. So once more, Amdahl's law is very pessimistic. It doesn't show the full picture and doesn't show the advantages we may get when we run in parallel. So from that time, yeah, I have shown some distance between Amdahl's and Gustafsson law. You can have a look later. Although the difference is not really big in when you look purely in the formulas, um, it just indicates that there is a larger potential in parallel computations than Amdahl's law predicts. And then you can see I have included here two papers which are relatively recent, where different um, parallel performance models have been um, studied and discussed. And again, since we don't really have the time, I'm not going to say much about them. I will show shortly on the something on the roof line. Um, Here it is. You see, since the time when Amdahl's law and Gustafsson-Barsis law have been discussed and first appeared, the architecture and how the parallel computers have been built has changed a lot, and the architecture is much more complex now. So we have all the caches, we have various cores with the non-uniform memory access, etc. So the model how to actually predict parallel performance is not easy at all. And here is one viewpoint you can think about. So when we should judge about the performance, we should first understand our algorithm. Is it memory bound or computation bound? As long as the algorithm is memory bound, we cannot reach the full peak floating point performance of the computer. And if that's our algorithm, well, we cannot hope that we will run on the highest speed of the of computer which is available. So only when our algorithm is computing bound, then we can reach that, and so on. So this attempts to actually try to find how to model the parallel performance of an algorithm is an open question, and of course it changes with time, and also somehow tries to reflect the way how the architecture changes. Okay, so we should also think about um, computational and communication complexity of our algorithms. We can, so the computational complexity is measured as a number of arithmetic operations we need to perform when we are doing a certain computation. And the communicational complexity depends on, um, of course, it depends on the hardware, but it also depends on the logical structure we imagine we do this computation in a parallel. So let's take a look. I have now to sum up n numbers. And I'm thinking about having as many processing elements as the numbers, the numbers I have to sum up. And I think I have this tree structure. So I have in each node of my tree, I have a number. And what I do in parallel, I sum up each two numbers. So I get a level 2 in the tree. Then I keep on doing summing up next to, going up to the root. And finally, when I come to the root, I have summed up everything. So now we can think about what is the communicational complexity and what is the computational complexity. So the computational complexity is clear, it's n minus 1. The communication complexity is log n because of the tree structure. So if I imagine this computation to be done in this case, I have my communication complexity, whatever I do, right? And in some way, we should be able to analyze the uh, computational and communication complexity of an algorithm in order to predict the performance and in order to see whether there will be a bottleneck or not. I'm going to show you the same operation done on a different logical structure. It's the hypercube. Now, of course, everything, if you have studied the little graphs, you see that the communication has to do with the diameter of the corresponding graph. And diameter is the longest distance you have to travel between two nodes in the graph. So it's log n. If you have a hypercube, the distance is the number of dimensions of the hypercube. And now we have the same task, or we have an even a more complicated task. We want to compute the scalar product of two vectors on this hypercube. So we have in each processing elements, we have two elements of the vectors, or a number of them. And then we see that with communicating once along each dimension of the hypercube, we are done. So my communication in this case is proportional to the number of dimensions. Of course, it has parameters about latency and how fast the communications, how fast the information is sent along the lines. But the diameter of the hypercube is much shorter than a binary tree. And this has to explain why in some of the supercomputers today, we have several networks. One of them is just following the hypercube structure to be able to do global communications, because the scalar product is a global communication. We have to, everybody has to send a message to everybody else and receive in order to get the resulting scalar product available in each processing element. Okay, I just want to show you, so let's see how is our time. I want to show you, last thing, one example, which you don't have to know much about the algorithm. But we have quite large problem size. And this is on one of the older clusters in UpMax. We have, these are nodes in this case. We have some kind of something which is called iterations. And this has to do with the computational complexity. Right? Then we can look at this time, which has to do how this algorithm, which is computationally optimal, it doesn't change with the number of, with the size of the problem. It changes, but the way how, so this constant number of iterations means we do constant number per degree of freedom, constant number of operations per degree of freedom. And we look at the time. So for instance, here for this size, I start with 32. Sorry, these are cores. And then I double them. And what do I want to see? Well, I want to halve my time. So from 120, I'm not halving the time, but I still can be happy. If I double again, you see, I didn't reduce the time. If I take even more, then I'm almost half. And you see that there are effects which are difficult to explain when you look at the performance. So why should we here have a halving the time and not here? And I leave this to a further discussion later on. Now I take a larger problem and I look at the time. So if I look here, it's almost half, and here is a half, here is not. What does it mean? That for this size of a problem, I should stop at 256 cores and I should not go further because I just don't do anything. I don't use the machine. I cannot load the machine enough so that I can get the performance. Okay. So this is my last slide from the previous presentation. I stop now, and we can um, we can open the new presentation. So let's see, I have to find and start with MPI itself. Um, Probably you have questions. I suggest we take them later because we have to go through the MPI construction so that you can almost start programming. So today's topic is basic MPI and some also very how to say the most important communications, which are point to point and collective communication. So we go to see how actually this is done in MPI. Okay. Let's see if you can see. I just want to mention that distributed memory programming is our basic framework, and we have memory which is local to each processing element. So whenever we want to read or write in the memory of another processing element, we have to communicate. And the standard for this nowadays is MPI, message passing interface. But it was not only the only one which existed, and I think it's good to know this. For instance, the first library which appeared historically is the parallel virtual machine, which is much more general framework for heterogeneous machines. And then through the years, there were different libraries which were specific for machines, like for T3E computer, etc. But as we will see, having a standard for that brings a lot of advantages. And MPI has become this de facto standard. Although there are more, there is something which is called BSP, which stands for bulk synchronous parallel, which exists, but it never became so famous as MPI. Okay, so here is a bit historical. So what is MPI? MPI is a layer between the programs which run on our processing elements, and as you can see, they have their own memory, and the communication network. So we send messages to between the processing elements, and they go through MPI. Then they were sent over the communication network and received whenever they were sent to. So this is how it functions. This is the paradigm. And as you can think about message passing is really like similar to a mailbox, a phone line, or a fax machine. So the process needs to be connected to a message passing interface, and this means that the sender must have the address where to send the message, and the receiving process must participate. It means it must have a mailbox where the message should come, it should have a telephone to answer, etc. And also has to have a capacity to receive the certain message. So MPI appeared in 92, Uh, and since then, there is a MPI forum which takes care of what kind of standards, what kind of functionality MPI should have, how it should be implemented efficiently. You can think that MPI is implemented differently on different platforms. Um, so the functionality has been extended through the years, and now we have different standards. So from MPI 1, we are now at MPI 3, which is available on UPMAX. So what is MPI? Well, MPI is a library. It's a set of routines which support point-to-point communication between pair of processors. And these communications, they have different modes. We will see that. They can be blocking, non-blocking, etc., which allow a certain flexibility in our programming. MPI has also something which is called a communication abstraction, and it provides a support for the design of modular parallel software libraries. So we can think that the system libraries should not interfere with the user programs, and they should have a different um, way of communicating so that the messages do not interfere. It also um, allows us to introduce logical architecture. We will see logical layout of the processors. And also it has a very rich set of collective communication routine, which allow us to communicate among a set of processors, a group of processors, without coding each individual send and receive between each pair of processors. So that's what we are going to go through and see what kind of functions we need to start. So the number of routines MPI provides is very big. So we need actually, to start with, we need quite little. And then the idea is that the more you get experience with MPI, the more functions you can utilize. Um, so the so if we have an MPI program, what does it mean? So we write one program, and a copy of this program is run on each processing element. So this idea goes very close to single program multiple data, or even multiple instruction, multiple data streams, because although we write one program, it does different things on each processing element. So, as I said, the code is written once, but it may perform differently on each process. And then the communication is done via MPI communication primitives, calls to MPI routines. Um, Here are some things to mention. As I said, it's one single program we write. The variables are private. We call the library. And what is important is that there is no magic in doing parallel programming via MPI. So you can think about the MPI like assembly language. You can do everything, but it costs. It's not like just a directive around a loop, and then somehow the shared memory framework does the parallelism for you. No, we are now the ones who have to see how the communication should be done, in what order, and how we can do this efficiently by calling MPI. Okay, so when you start MPI, this is what happens. So the program is bound to the multiple instances we have said we want to use. And then it is executed in the separate process in their own memory. So the messages, how do we communicate? We communicate by sending messages, which are packets of data, and they are moved between the processors. And of course, we need a certain information to be able to do this. Namely, we have to know who is sending, uh, where is the data to be sent, the location or the address of that, what kind of data type is that, how long it is, who is going to receive it, and of course, we need information where to write the message when it is received. So um, we start with the simplest thing to way to communicate. This is point to point. I have two pairs of processing elements or processors. Don't mind the name of that, and I want to send a message from one to another. And so both ends actually participate in this communication. So how can we send this message? And we will see that the way how the point-to-point communication can be done, we have several options. We can do this blocking or non-blocking. Blocking means that I don't do anything else before the communication takes part. I can do it in a non-blocking fashion. This means I am the one who sends. So I send it and I don't care whether it has been received or not. So I continue doing my own things. And this setting allows me to overlap communication and computation. So this is a very important issue. I write it here. So you should think about this to use blocking or non-blocking in the implementations we will do. And there are other versions. So each command has several possible types to do this. And we can just mention, as I said, blocking. We start with this. If return from a procedure we call MPI, indicates that the user is allowed to reuse the resource, only the return, when we know that the communication has taken place, we can reuse the memory. And the non-blocking is something which allows us to uh, be more flexible. So the procedure may return before the operation has completed and before the user is allowed to reuse the resources. So we can continue with computation, for instance, or do something else. Local and non-local, it's more to think about um, how the completion of a procedure depends. It's only local executing process, no communication, or some communication should take place and communicate with another process. And the collective types of calls where we have communication between a group of processors, all of them or a group, and all of them are executing the communication of different type. We will see them. Okay. Now we come to programming. So I already mentioned that the number of functions in MPI is very large, but basically to start programming, we need only 6 of them. We initialize, then we do two things. We have to determine how many processors we have at our disposal, 2 or 4 or a certain number. And then I want to know, or my code wants to know, who am I? So my process number. And there are two commands to get this. One is MPI com size and the other one is MPI com rank. So the rank is the number of the process I have. And they are from 0 to n minus 1 if we have n number of processors. Then I have two commands at my disposal, send and receive. So I can do everything with that. And then I finally, when I'm done, I finalize. I close everything and all MPI to finish the code, terminate the code successfully. So those six are enough. And one more thing, uh, we have a header file to include. We will see what it, you can see, you can access that and see what it contains. And this is how we initialize MPI. We include MPI in it in the beginning of the code or before we want to use MPI. We have 2 more minutes, so I can do a little more. MPI has its own data types, and they are explicitly used in the MPI calls. Why we need that? Because of portability. So internally, um, thanks to MPI and these data types, we can run MPI on different computer platforms where the um, doubles and integers, etc., may be defined in a different way. Okay. So this is something to know, and this is included in the header file. Uh, we have also handles at our disposal, and we will see how they are used. Um, Also, we have a communicator. This is the last I say before the break. Um, so the communicators, you can think about those communicators as orthogonal message passing universes. I like this expression. So one communicator can be a phone, and the other one is the mail system. So if everybody has a phone, you can reach everybody via phone, but also you can send a letter and it will arrive. And this is very important because the user messages will travel in one communicator and the system messages will travel in another communicator. And these are um, completely transparent to the user. Okay, so the communicator most used, we are going to probably start with, is MPI COM world, which is the default, and it contains all the processors available when we run an MPI routine. So MPI COM world is a handle, and you can see it in the header file. So I think it's a good time to stop. We take 15 minutes break and we continue after that. I have some problem showing the screen. Just a second. Okay, here we were. So I'm talking about some communicator which contains all the processors. And how do we actually start the whole story? So we have written a program, we have compiled it, and then we say MPI run, and then we say -n, for instance, 4, and then the code, the executable. And this is how we say to the system, we need 4 processing elements. So all these 4 will come into the COM world, and we can communicate between them. So they will be from 0 to 3. The two commands to get who am I, my rank, and the size which has been asked for, as I showed you with the command MPI run, they will appear in a variable size. To finalize, we just write a command finalize, which takes care, we can abort if necessary with some certain error code. And here is how the first MPI program could look like. Uh, Almost all courses contain this program. We have, you can see, we include the header file, we initialize MPI, we get the size, we get the rank, and then we just print hello world and finalize. So the result of this, oh yeah, how we compile. Usually it's convenient to use a make file. So the compiler is MPI CC. We can have a compilation flag, libraries, and we compile and then we run hello. We run hello, for instance, on my laptop. I have two cores and I get hello world twice. So every core will write hello world because that's what the code is doing. However, I don't know who is writing what. And the message is the same, but I don't know who has written this first or second. So we can probably do a little combination, modification of the code. For instance, every process can write world. We are so many of us, and I am that one. So everybody prints the size and says who is that, and finalize. So the result of that with 4 cores will be like this. So you see, the message, we are 4 of us, has issued by all process, and then you can see that the messages, they come in order which is not by any mean from 0 to 3, but in any order, which makes actually you can already feel that because of this, which is a kind of random, it's difficult to debug a code, right? So it's rather messy, and that's how it is. So the order of the messages from a parallel code will come every time. It can be different. Okay, we start with communications. The slides contain more information than we can cover, and um, I I will mention the most often used. The rest is for reference, and you can always have a look at that. Okay, so we have initialized and we know how to get the total number and who am I and finalize. Now we try to send and receive a message. Before we go to the particular syntax of each operation, I mention here what do we actually have as a type of operations. And this is what we are supposed to cover today. So the first one is point to point, from one process to another. The other possibility is broadcast, one to all. And then we have, so this is, broadcast is one and the same message from one to everybody else. When we want to move a different message from each process to every other, this is all-to-all broadcast operation, and we have it. We can have scatter and gather operations. These are collective operations. So one source is sending to everybody else, or is gathering from everybody else. So these are dual to each other, gather and scatter. And finally, we may want that we have a multi-gather and multi-scatter. So this means um, we have a different data sets sending to every process or gathered from each process. So this is the probably most advanced collective communication.
Pardon me. Uh,
We start
well,
with point to point, and we will mostly consider blocking and non-blocking send and receive operations. And for the blocking version, the send call blocks until the send buffer can be reclaimed. So it's blocking. We cannot reuse that um, memory for something else. For the non-blocking send and receive, they are particularly created to enable overlap between communication and computation. So the code which issues the send command can continue before actually we are sure that it has taken place. There are other types of um, communication modes, standard, buffered, synchronous, ready. They are explained in the slides, although they are not that essential to our to the course. So, for instance, I don't think we will use anything more than standard in the course, although it's good to know that there are other types. So I have some information about each of them. Um, for the communications, we of course need to provide, as I already mentioned, more information. What kind of data type we are sending and how long, how many instances of that. We also have some kind of particular tag flag which is associated with send and receive commands. You can imagine that one process may send to another several messages, and when receiving them, they have to be matched. So we have to know what I'm receiving now, and this is the tag which helps us. Tag is an integer, and we can follow, we can connect a send and receive command via a tag. There are certain possibilities where we receive from anybody, and it's quite interesting because actually um, the tags are heavily used in the communication network to prioritize the send and receive commands, rather the message transferring. It is important to notice that if we use the tags explicitly, um, the order of send commands is matched with the order of the received commands, so they don't overtake each other. Um, yeah, so this is what I already mentioned. The messages do not overtake each other, and they are received in the order they are sent. Um, the sent and received commands, they should have the same data type. This is not always true for some other commands, but for point-to-point send and receive, they have to match. And in this case, it's not possible for a matching send and receive to remain hanging. That's that's something which ensures correctness of the code also. Okay, so the message envelope, it's a source and destination. Uh, what is the communicator and what is the tag. And if you look at, let's see, how does it look? This is the command, MPI send. This is the memory address where my data is, how many elements of this particular data type I'm going to send, the destination, I'm sending to processor number this one, this is my tag, and the communicator. And now you see that this is the send command is defined uniquely. So you can see some, this is the basic for, and it's called blocking send. There are, as I mentioned, different types, which I will skip talking about them. Synchronous, for instance, this is an extra, this is going to be executed slowly because the send will not complete before the receiving processor acknowledge that it can be, that it is received. So then we proceed. So this is synchronous. This is for safety of the code running. Buffered, this means that we must use a system buffer, which has to be defined before or allocated. So I go over this. Ready is also something we are not going to use very much. We are going to spend some time on non-blocking send and receive. So what does it mean? They are so there is an I letter in front of the send and receive command. And they also have several modes, which are similar to the blocking send and receive, non-blocking, synchronous, etc. Ready. So what is this I send for? So you see, I've told the system I want to send this message from this address, and I issue the send command. But then I'm able to continue computing, and that's why it is non-blocking. So the blocking send, I will not be able to proceed with the rest of the code unless it has taken place and I can reuse the memory where the message to be sent was. Now I can continue computing and doing other things. And at some point, I have to ask the system, well, can I now use this memory again? Has my send taken place? And I have a certain MPI calls to do that, to get this information. Of course, I may, let's see now, I can show you. So now this is, we will see the syntax. I'm sorry, I think I have to say something about the receive. The receive command, in this case, the blocking receive, has a similar structure as the send. And it's just absolutely logical where the information should be written, how much of certain instances, from whom I am waiting for to get the message, and the tag communication. And here there is an extra parameter, which is the status. So if we go back to send, here it is. So I'm sending to the destination, and I tell where the information to be sent is, and a tag, and then the receive command is I'm waiting from the source, and whatever information comes related to that tag from that source within the communicator should be put in that address, which is named buffer, and it should be that long of that data type. So those should match. The data type should match. So here is an example. If my rank is not 0, I am waiting to receive things. Otherwise, I'm sending. So you can see now that processor 0 is sending messages to IPE. Here is the destination. It sends some kind of integer, one integer, via the standard communicator with 3 different tags. And so that's process 0. And the other guys, they receive. So if I'm not, and now you can see that this is the program I have written. Of course, on a different process, it will behave differently. So only processor 0 will send, and the other will receive from processor 0. Okay. We can combine them. I have to check the time. Okay. Sometimes it's very convenient to combine send and receive. And in many algorithms, this can be very suitable. So I'm going to draw a picture. How does it work? But let's see first what kind of parameters we have. We have, of course, a send buffer and count and data type. We have a destination and a tag. And then we have a receive buffer and count and type, from whom, another tag, communicator, which is only one for the operation, and some status. And let's see what I have. Before I show you some example of that, I want to draw a picture. So imagine that we have processors in a row. And the easiest probably example to think is that I want to, sorry, this was not very good. I want to send, so this is an array of elements. I want to send this column to the neighbor to the right and put it here. And I want to do the same for all processors. This guy wants to send to its right neighbor and put it on a certain place. So put it here so that we don't overlap the existing rows and information. Oops. So we have an array which is extended by some hollow columns and rows. Okay. So you see, for this particular structure, I can use send and receive very easy. So each process has a send and receive. It sends to its right neighbor the last column and receives from the left neighbor a column which is put on some particular place, not destroying the existing information. It can be done, so the last one obviously wants to send here. That's what the code will be showing. And it's very easy to organize because I know how many processors I have, and I'm thinking they are in a ring as a logical structure. I don't care how they are on the architecture, but I think in my logical organization of my code that they are in a ring. And I can do this operation for all of them by send and receive. I can have the same receive, and so you see here that my processor which is sending is different than from the one which is receiving, but I may have the same. So I can do this, um, sort of between the neighbors. I can also do this with send and receive. And send and receive is a more general uh, uh, call, MPI routine, which allows even to have a different data type. But forget about that. We can think about the same data type. We can think about some part of matrices which we are sending around. Okay, so let's see. There is a little code which is included here, which is doing exactly what I showed you on the picture. So there is some logic which tells me who is left, who is right, related to me. And I'm sending to the left and receiving from the right. It doesn't matter what my organization is. And of course, I may secure myself that I really have a neighbor left, right to think about the ring. So I have two different buffers, and in this case, integers, 10 of them, etc. So this is, again, one operation which is combination of send and receive, which may facilitate particular communication pattern. This one is, I have the results of this. So, yeah, I don't know. Maybe we can discuss the examples a little later. So I first go through the material and then we can talk about this. But actually the code is very simple. I have two, in this case, the code is limited, of course, just to illustrate what is happening. And we set certain values in the two arrays, on the two processors, which are related to my ID, which is my rank, and it's different on the two different processes. And then with the send and receive, I exchange information between the two. So if I have in the beginning, so you can see here, before I had on P0, I had an array 5, 5, 15, 15. And on P1, I had 6, 6, 16, 16. And then I have told, I have fixed the send and receive. And the result is that this line goes here, and this line goes here, and that's what I see. So the first is untouched, and this is untouched, but they are exchanged. So that's what the code is doing. And of course, we have non-blocking send and receive. Again, the idea with non-blocking send and receive is that I can overlap communication and computation. However, as I said, we need to know when I can reuse the resources, when this command has taken place. And that's why this non-blocking send and receives, they have an extra argument, which is called a request, and I can check on this request. Or I can wait till completion of the communication. How does this work? I can wait till all requests are done. I may have several commands issued and each has a certain request. So I can wait till all of them are done, or I can check whether a particular request has taken place, a particular operation has taken place, and then I can continue. So I send do something else, and then MPI test. If okay, continue. Else, do more and check again. Or wait. That's the idea. So here is an example. I issue two send commands which are non-blocking, and I have two requests. I have actually an array of requests, 1, 0, and 1, and I issue two I send commands. I receive commands, and then I do some computational work. At some point, I say, wait till the requests are done. So you see, once more, the biggest advantage is that I have the possibility to do some other work, which is, in this terminology we have here in the parallel computations, it's overlapping communication and computation. So while I'm doing this work, the system is free to communicate. And luckily it will be done before I wait, I issue the wait command. So when I issue the command, everything is done so I can continue with the code. So what is this example for? You see, I have blocking send commands, and I have non-blocking receive commands, which are matching the tag and the source. So it's rank 0 who sends, and the receiver is waiting from source 0. And pay attention that my tags are in, so the two commands, the order of the two receive commands do not match the order of the send commands. And if it was a blocking receive, this will be a deadlock. But here, it will not cause that. And then we have, when we have received, so these are rank non-zero, guys, then it will continue for the code which is to be run on rank 1 in this case. here is a little bit more text. This is another type of communications. These are also point to point. And I'm mentioning them, I think, uh, when we look at the parallel debugger, there will be illustration of persistent communication requests. What you should remember is the following. Sometimes in the code, I have a fixed communication pattern. Once and forever, my processors are communicating in a very determined order. Number one is sending to number two, and number two is sending to number four, and whatever communication pattern we have. And we can sort of describe this communication pattern in advance and then reuse it. The plus is that the communication time, the communication overhead will be diminished. How we do that? We, of course, need to first sort of set up the persistent communication. We have to initialize, and um, you can see that these are for send and receive, and then we can use, then we can the once it has been initialized, we can reuse it as many times as we want, again leading to a lower communication overhead. It's very nice that the debugger actually makes a graph of our communications, and we can see this a particular persistent communication request. So first, as I said, this is step one. We create a persistent communication pattern. Then we start it. And this can be done as many times as we need. We have to wait till it is done. And when everything is ready, we deallocate the resources. So it's a nice possibility. And you can see how it is, what the syntax is. There is one example. You can have a look. So nothing very special. Here is a initialization of send and receive. And then we have a start on receive and send. And then we wait till it's done. Finally, we free the resources. Okay, another code. I want to go over the collective communication. We have 10 minutes, and this is definitely not enough, but we go and have a look through all them. So I mentioned them already. Broadcast, gather, scatter, all to all. And we also have an operation which is called the global reduction. And this MPI calls enable us to do operations like sum, maximum, minimum. And this means, because they are global, that all the participating processors know the result. The barrier synchronization, so it's a barrier command, allows us to sort of at somewhere in the code to wait till all processing elements come to this barrier line in the code. And this is a very expensive synchronization of the code, and it should be avoided as much as possible. So now we can see how those collective communications are used. So barrier, nothing to say. So everybody waits till they come to this barrier line. Nothing very special. Broadcast, also exactly what we expect. So we have a source, and the source sends one and the same message to all others. What do we need? Well, we need where this is the address, what we're going to send. It's called coefs, it's a variable. We say how many, they are double in this case. Who is sending? Processor 0, and within this communicator, this means to everybody else. Nothing very much to comment on. We have the example is easy, but I think I have a demo to show you. Actually, in the next to the slides, you have a zip file with 4 communication routines: gather, scatter, uh, broadcast, all to all. You will see them. You can see how they're used, and you can run them. If I have time, I will show you. Gather. So we have information which is uh, in all others and has to be collected in one of the processors, and we say who is going to, in this case, receive the information. And scatter is exactly opposite. I have information possibly different in one process, and it is sent uh, different information to different process. You can think about a vector or a matrix, and pieces of that are sent to the other processors in order to split the data. All gather, and all. So what is this? Okay, all gather. So you can see that the processes have different information containing, and they, at the result of the iteration, they collect, each of them collects all the information from the others. So it's just to make our programming easier. For instance, I have an array. I have to, so this is going to be a gather command. This means I have to ensure where the information which I'm gathering will fit. And that's it. MPI gather. That's what I'm providing to the others, and this is where I collect it. So let's see. All to all. Now you can see that each process has a different information to be sent to everybody else. So process number 0 is here, and it has some information, and this information is sent to all others. And similar to information which is particularly available at process number 1, and it is distributed over all others, etc. So all to all, just one command, and it's quite convenient to for such type of information if we need. This is probably collecting a result of some computation. Reduce or all reduce commands, which are, you can see what the names they have. So max, min, sum, the product of elements. We have also logical operations which are global, and these are very convenient to compute scalar products, for instance, or find a minimum and maximum, of course. So once more, these communications are global. They involve all the processors, and the result is provided to all of them. We need to time the code, and this is how we do that. So we have MPI W time. So you should be careful. It returns a floating point number of seconds representing elapsed whole clock time since some arbitrary point of time in the past. So this means to get the time for a particular part of the code, we have to subtract the result of between two consecutive MPI whole time commands. So it's written explicitly here. For instance, we fix the time in the beginning and then we call W time after a particular part of the code, then we know how much time, the difference is telling us how much time this takes, etc. Now let's see. 3 minutes. Let me show you a little bit. So, just a second. Seems I have to share the whole screen. So let's see. That's a directory where I have the codes you have, and you can see more codes here. But what you do is you make them if you unzip the the file I have given you. So you get the broadcast, scatter, gather, all to all, and all these little demo routines are written by Malin Schelen, which was helping me previously with the code, with the course. So you can see all of them. So now, okay, I have compiled them. The make file is nothing special. You can see it. So how do I run some of them, of those codes? For instance, I have two cores, as I said, very poor MPI run. So I want all of them. And then I run broadcast. And it complains, which it didn't before. So let's see now. I have to lift it a bit because I don't see what it is. Oh, shame to me, but it works. So before process 1 has 0 value in a certain address, and the one who is broadcasting is process 0, it has 888, and obviously after the broadcast command, it has received what it was broadcast. And similarly, you can see all others, you can see the codes and you can have some idea how it works. So let's see now. This is all for today. I stop recording.